So good afternoon. I would like to thank the organizers for giving me the opportunity to share the status of the Electron Ion Collider, which we're building at Brookhaven with you. So the outline of my talk is I'm going to give you a short introduction, motivation, design overview, and then discuss some of the interesting and challenging features of this machine and the way we are dealing with them. Before I come to schedule, discuss somewhat international collaboration and come to a conclusion. So the nuclear physics community has worked out a nice white paper in 2015, and they condensed this in this list of requirement of physics goals. And so it can be even further condensed by saying we want to understand the mass of the proton. We want to understand where the proton spin comes about. We want to understand how the constituents of the proton and nuclei are distributed in space and in momentum. And finally, we would like to shed light on how the ever-growing gluon density with low x is saturating. And so this is an exciting physics program, and this results in these requirements here. We need very large luminosity, 10 to the 34, with some up to 100 inverse femtobarn of integrated luminosity. We need to collide fully polarized beams, 70%, both hadrons and electrons. And we want to operate a machine over a large set of mass energy range, 20 to 140 GeV, large range of ion species. There's only one detector in the project at this point, but we have to make sure there is the possibility of accommodate a second one. And one of the important features is that this machine needs a very large detector acceptance. So we have to compromise the accelerator design to make that possible, and of course good background conditions. So these goals they match or exceed the requirements of this long-range plan, and which was also endorsed by the National Academy of Science. And our design, we claim that meets these requirements, and so far everything which we have investigated seems to say that that's true. So this is an overview of the design. So here, the Electron Ion Collider will be based on existing rig. It's still operated. It's well maintained. It's already 20 years old, but is continuously upgraded and is operated at its peak performance every year, more luminosity. And the EIC, I should say this upfront, is a collaboration between JLab and Brookhaven. Built in Brookhaven. So we take the two hadron rings of RIG and form a new hadron ring for the EIC. And with using the existing superconducting magnets, we operated with a lot of bunches, large beam currents, 1 amp, 3 times larger than RIG. We have a bright vertical beam emittance of only 1.5 nanometers and flat beams, which is quite unusual for hadrons. And we require to cool the beam during luminosity operation with a high rate in order to maintain the beam parameters and the luminosity. So we have to add an electron storage ring, which will operate at up to 18 GeV in the same circumference, same tunnel, same circumference. It has a large beam current, 2.5 amps. We need superconducting RF. We radiate 9 megawatt of synchrotron radiation power, and we put it as a limit. We need to inject fully polarized bunches, and I'm going to explain why. In order to have to allow that, we need a rapid cycling synchrotron, which provides us this fully polarized bunches at full energy. That's quite tricky, and I'm going to discuss this a bit. And then, of course, an interaction region, which is dominated by the detector in its acceptance requirements, and but needs superconducting magnets. We have crossing angle and needs scrap cavities, as has been discussed yesterday by Jürgen. and spin rotators, and a lot of forward hadron instrumentation. So RIC, which looks like this here in today, will look somewhat like this, with 3 rings, this superconducting, one of the superconducting hadron rings, and then 2 more new electron rings. So this is the parameter list of the machine. So as I said, the center of mass energy range goes from 20 to 140. So this parameters here is the peak luminosity, which is obtained at 100 GeV center of mass. So we are pushing beam currents and also the strength of the interaction between the 2 beams at the collision point to a maximum. And we also make the choice of a flat hadron beam. And then we push the beam population to a maximum, which allows us to have stable beams, maximizing the bunch distance this way. This gives us 1100 bunches and allows us to operate with an emittance that is manageable by employing strong hadron cooling. That gives us a luminosity of 10 to the 34. And you see here is how the luminosity changes with center of mass energy. This is the peak here at 100 GeV. If you go to higher, we have to increase the electron energy, and so we are limited by synchrotron radiation and the RF power to compensate it. At lower energies, we are limited by the rigidity of the beams and more sensitivity to the beam-beam interaction. Okay, so let's discuss the collisions in the machine. So we need a crossing angle of 25 milliradian because we want to collide only at the interaction point. We uncompensated crossing angles in this parameter regime would not be possible. We would lose a lot of luminosity geometrically. So we need crab cavities to compensate that, and also to compensate some of the detrimental dynamic effects which go along with a large crossing angle. So we have developed these crab cavities, and yesterday pictures have been shown of various models. So this is the one we're going to go with, is a crab cavity developed by JLab. We have two frequencies in order to linearize the crab kick. You see the issue is down here. Since the field dependence is sinusoidal in time, the head and the tail get somewhat less kick than they should. And so this is quite detrimental. The beam gets separated at the head and the tail, and it introduces additional resonances and emittance blow up. Second frequency helps to mitigate that. So, and of course, once the hadron beam is blown up, the electrons are now too small, and this small electron beam blows the hadrons up even more. So it's a runaway situation. Crabbing has many challenges. One of them is that we are very sensitive to phase noise in a crab cavity, because that induces a dipole kick at the hadrons and the electrons, so they get separated. The center of the beam gets separated in the interaction with in a random way, and that is very detrimental for the hadrons. Electrons do not suffer from that. Okay, the interaction region then looks like this. So this is the typical plot here with an exaggerated vertical scale. You see the detector in the middle. We need some final focusing magnets around. We need crab cavities, we need spin rotators, and there's a lot of additional instrumentation. For example, there's neutron spectrometer and a lot of Raman pods along the beam pipe in order to detect small angle scattered particles. So quite complex. So the superconducting magnets, there's not much space. So we have in one coil that combined magnets side to side for electrons and hadrons, of course, quite different strengths, both superconducting. One particular interesting magnet is the first magnet here. This is a spectrometer magnet, a large aperture superconducting magnet with the aperture in air, which is instrumented, the hadron beam pipe goes through, and also the electron beam pipe, that needs to be shielded against the spectrometer field. And we also put some windings, some quadrupole windings around that, so to give the first focusing lengths for the electrons. One technology which we use besides the typical colored design for superconducting magnets is this direct wind methods, which has been developed some 20 years ago. It has been employed at several places now. So it's a very flexible technique, very cost effective. For example, it allows us to build such a double helix quadrupole, which is even tapered and with extremely high field quality. So that's an interesting technique, which is without which it would be very difficult to proceed. So this is how the interaction region looks like. The detector here is the magnets, and also you see that the rapid cycling synchrotron also has to pass to the detector. So another issue with high luminosity is we need to make the beams small. We focus them very strongly. Then the corresponding beam sizes in the final focus magnets is very large. And so that gives rise to chromatic aberrations of the beam optics, which is very detrimental. We would not be able to store a beam if that would be left uncompensated. This requires a fairly sophisticated scheme of sextupoles to remove this to up to order 3 in the chromatic distortions. And for now, we have found a satisfactory solution, even with 2 detectors. This makes a fairly sophisticated lattice design in which we have to also include the requirements for beam polarization. I'm discussing now high beam intensity effects. So as I already said, we need 9 megawatts in the peak luminosity operation at 100 GeV center of mass and we need a voltage of 64 megavolts at 18 GeV. So we need 18 single cell quadrupoles, superconducting cavities, which are driven by solid state amplifiers. So the electron bunch charge is quite high, 28 nanocoulombs. So that means we have to carefully minimize the impedance in the vacuum designs. Tapers have to be limited in their steepness. Shielded bellow is a critical design, which I'm going to discuss a bit. And the cavity needs to be quasi-single mode in order to suppress higher order modes, which would affect the beam stability. For using silicon carbon type beam pipe absorbers, they have been already employed in the KKB. So the hadrons also have some issues with high intensity. The RIG beam pipe, the cold beam pipe, is stainless steel. So the resistive heating from 1 amp of beam current going through there would be an unacceptable cryogenic load. So we need to put in a liner which with a better resistive material with copper. In addition, there is an effect that ionization of the rest gas leads to electrons being accelerated by the beam fields to the vacuum chamber. There it releases several electrons. They get accelerated by the next bunch, and so a cloud is forming. And this so-called electron cloud effect is one of a limitation, and we need to make sure that the surface of the beam pipe has a secondary coefficient of less than 1, and that is achieved with a amorphous carbon coating. And this is a technology which has been developed by CERN. So you see here the single cell cavities, and we have 18 of them. And this is the picture of the higher mode absorber. So it's a silicon carbon ring here in a copper mantle, a water-cooled copper mantle. Critical is also the input power, the input coupler for this cavity. We need to put in almost a megawatt in each cavity, so we need 2 couplers. And this coupler has been tested, has been built in R&D, and it looks so far quite good. So this is a picture of the power supply of the RF power supply hall with solid state amplifiers. So you see, it's quite an installation. So each cavity gets its own 800 kilowatt amplifier. I'm coming to spin now. So we need high spin, 70% average polarization in both beams. And in the electron storage ring, the synchrotron, due to synchrotron radiation, the polarization would build up slowly by the Sokolov-Turnoff effect. Spin flips to induced by emission of a photon. But that process is very slow. It is also present in a real machine. It's hard to get, let's say, above 60% due to imperfections. But we need something like between 70 and 80%. So also the buildup for polarization is very slow. It's in a time scale of hours for the lower electron energies. And so that buildup would also work for spin which are anti-parallel to the magnetic guide field. But in order to deal with systematic effects, we need to have both spin directions present in the same fill to discriminate against systematic errors. So self-polarization doesn't work, so we need to inject into the machine fully polarized bunches, which are created by in a polarized source and is preserved during acceleration in a rapid cycling synchrotron, and that's quite tricky. So then we need to also still compensate carefully the many effects which are destroying polarization in order to maintain a high average polarization of 70%. So we need careful orbit control, extremely careful compensation of the coupling, which is caused by distortion of midplane symmetry of magnets, and a careful choice of tunes for the spatial coordinates and also the spin coordinate. And also the detector compensation needs to be carefully compensated by rotated Godbole. There is no space in this detector due to the acceptance requirement for a compensating solenoid. So, so where we stand is that sorry, I have difficulties here. So this is the polarized electron source. It has been already built in an R&D program before the project, so it's now ready and operating. It's fully performing to the requirement of the EIC, and it's even possible also to operate that beam with fairly high average current. So it would be actually also interesting for other applications. So that's already existing and can be carried over to the EIC. Then the beam goes through a 400 MeV S-band linac before it's injected into a synchrotron. Now, in a synchrotron, we have everything at 50 MeV. We have a depolarizing resonance when the spin precessions per turn is an integer that would destroy polarization. So that can be compensated by a high periodicity of the lattice. So with a very high periodicity, these resonances do not appear. It has actually been shown in the AGS where certain resonances which were suppressed by this 6-fold symmetry of the AGS. Now here we need something like close to 100% periodicity. So how are we going to do this in a geometry which has a 6-fold symmetry? So the trick which we are applying here is the arcs are as periodic as possible, and the straight sections are configured as unity matrix for all beam coordinates. That way they become invisible to the beams, and the beam thinks it's in a perfectly 100-fold periodic structure. And that concept works. It has been extensively simulated, and up to the extraction energy at 18 GeV, we have almost no losses, even with realistic errors in the machine. So that's an interesting machine, and the beam is then injected into the electron ring. Still, since the average polarization is only about 60%, and we also have actually bunches where the polarization has the wrong sign, the polarization would decay very quickly from this initial 80%. And in order to preserve an average polarization of 70%, we have to keep injecting, replacing the bunches by kicking one out and taking a fresh band in, and every bunch is replaced every 6 minutes. So which means we have to inject a new bunch in this machine during luminosity operation every second. So that's quite a challenge for the injection system, mostly a problem of keeping the parameters under control, making sure we don't distort the beam operation. So the polarization then looks like in this picture. The decays is refreshed and decayed and so forth. So for hadrons, RIC has a successful polarized proton program, so I'm not going to discuss that. It uses Siberian snakes, achieves up to 60% polarization, and in ERIC we will add some additional snakes, which should give us then up to 80% polarization. We have recently added a polarized helium-3 source, which is then integrated in the electron beam ion source, and that should give us also up to 80% helium-3 polarized. And we convinced ourselves we can accelerate that the same way as protons without losses. So that is an interesting feature. There's also foreseen that we will have polarized deuterons, and for that we still need to design a polarized deuteron source. Coming to hadron cooling, at high energies, cooling of hadrons is really a challenge. Electron cooling usually works only up to a few GeV, and that's already very difficult. Recently, we have demonstrated that you can also provide cooling with a bunched electron beam in RIC, so that worked actually well in a recent low energy one. But at energies up to 275 GeV, that is not feasible. So we have to come up with something new, and the new thing is called coherent electron cooling. Why we need to cool the beam? There's interbeam scattering, which blows up the beam. Interbeam scattering is Coulomb scattering within the bunch, which is then relativistically enhanced, and that leads to emitter scores in all planes, or longitudinal and horizontal mainly. And so we apply this coherent electron cooling, which you could see is a cousin of stochastic cooling. So you work on the fluctuations, but you use an electron beam instead of pickup, and you use dynamic effects of the electron beam instead of an amplifier, and use the electron beam again as a kicker. So that is the electron beam picks up some fluctuations in the proton density. That energy modulation of the electron beam is then transformed by this section here, where we induce microbunching and cause a sharply peaked electron density at the position of the original fluctuation. Then we combine electrons and hadrons again here, and the peak in the electron density works against the energy spread and the betatron amplitudes of the hadron beam. It's a small kick only. You have to repeat this many, many times, and we can achieve with this scheme about 2.3 hours of cooling on paper. So we call this coherent electron cooling with microbunching amplification. We need 100 100 milliamp electron beam, 150 MeV. And there is many challenges associated with that. One of them is to keep this hadron beam and the electron beam synchronized while they're going through completely different channels. So we also need pre-cooling because the cooling would be too small to make the beam flat. So we need to make the beam flat at injection using bunch beam electron cooling, and that cooling facility is integrated in the strong hadron cooling. So this is how this facility looks like schematically. So you have an electron energy recovery linac here, superconducting 5-cell cavities. We inject that beam into the hadron channel. They propagate together. The electrons pick up the fluctuations. Then the fluctuations get transformed into a density peak and amplified. And the hadrons get combined with the electrons at this point here, and where the cooling kicks before the electrons take place, before the electrons get returned to the EAL to extract the energy for new injection of new electrons. This is probably running out of battery. Oops. Okay, so this is the one challenge is also to make sure that the electron beam, which is used for cooling, doesn't have any structure which it could obtain during acceleration or during the bending structure and microbunching, which is not supposed to happen prematurely. So we have this sophisticated injector, and so far the simulations indicate that we can produce an electron beam of the required quality. As I said, the electron cooler is for low energy cooling. This is incoherent electron cooling is integrated. This cooler uses the same electron source and the pre-accelerator, and also the whole beam transport system and the cooling channels with the strong hadron cooling facility. So that way we save cost and space. So I'm not going to talk about the detectors. They have a very strong instrumentation in the forward and the backward directions in contrast to, let's say, plus-minus colliders. So, but we do have, I want to point out that we have the experimental halls for this detectors available at this point, occupied by the star detector and the new upgraded Phoenix detector, which is going to be operated up until FY25. The schedule, so we received, I'm not sure whether you're familiar with this critical decisions for DOE projects. So we have CD0 to CD4 when the project is completed. We received CD1 last year and are now in the middle of the design phase. We are entering the engineering phase of the component at this point. We aim for achieving CD2 or CD3A in early FY25, early calendar year 25. And to start with the procurement of some of the items, and CD3 at 25. At that point, the RIG program will be completed. We will start to dismantle some of the and remove some of the RIG components which are not needed anymore, and start then while we are constructing the components for the EIC install. And we have the end of the project occurs in two phases. In about FY22, we have a CD4A in which we will start to operate the machine with the detector, starting learning how to take data and providing first physics data, while we are still completing some of the hardware which would not be useful in the early stage of the project. And Okay, so this brings me, no, I jumped over this slide here. Let me just say a word about international collaboration. So there's a large, as already pointed out yesterday by Jürgen, there's a large interest in electron-ion collider. EIC has a worldwide community which is involved in discussing the physics, and detector collaborations have been formed. And that is a growing trend. So this will be a truly international machine. We are also hoping for contributions to the accelerator from outside, but so far this has not been is not been firm. But there are many discussions going on with our colleagues in other countries. And that brings me to my summary. So the EIC is one of the most complex colliders because of all these requirements which have to be fulfilled at the same time. That makes it really very hard. So far, the challenges to design the accelerator have been met, and the global design is completed, and we now have a solid base for an engineering design. R&D for some critical components, superconducting RF, other RF components, vacuum, polarized electron source, that made very good progress. And the engineering has now started. So we look for collaboration with scientists and science institutions worldwide, and the scientists and engineering contributing to EIC are developing now into a strong and competent team that will develop the EIC project. And that is all, and I'm ready to take questions.
Thanks a lot for the wonderful talk. Questions? Govinda, yeah.
Sorry, this is some technical. At the end, you mentioned this is a 2-point was ready for this EIC. Will you have only one experiment or 2 experiments?
So the project has only one experiment, but we have been done some preliminary design on a second interaction region and a second detector, which has a slightly different emphasis, probably favors more the lower energy part of the physics program. But costed at the moment, and part of the project is only the first detector, which is an all-round detector which covers the entire physics range in an equal way.
Okay, thanks.
Any further questions? Yeah.
Yeah, you did not say anything about the detectors, but do you have anything like B tagging, tau tagging in plans or for the detector?
So of course there is a detector which is part of the project. It's being developed in parallel to the accelerator. I mean, I'm not prepared to tell you about all the systems, but there's a lot of, as I said, forward colorimeters, forward detection, particle identification, and so on. So much more heavily instrumented than, let's say, in a plus and minus typical plus and minus detector. And in addition, we have Roman pods along the outgoing hadron beam pipe. We have a neutron spectrometer. On the electron side, we have a tagger to tag electrons which are scattered off the collisions. So it is a very, let's say, a detector with many, many subsystems. Of course, the typical things, microvertex detector, a main tracker and colorimeters, hadron colorimeter, electron colorimeter, and so forth. Solenoid field is not quite decided, but it's going to be 2.5 Tesla.
So tentatively, when these things can be will be made public, like the performance, like timeline?
So there is a design report, a conceptual design report, which was published last year. sorry, 2 years ago. Time passes.
Yeah,
In August 20. So we are in the process now of writing a technical design report. The conceptual design report has already quite some detail about the detector, but since then we have had a call for collaboration, and we have collaboration has now formed. They're working on detailing out the detector, and details of that will be available in certainly in the preliminary design report.
Well, he's reading the question.
Okay, yeah, so I'm not sure whether I mentioned the RF frequency. 591 megahertz is the frequency of the cavities, and so we will procure this in industry. So the market for solid state RF amplifier is growing, it seems to be, whereas klystrons are becoming more and more difficult to get. So I think for machine in the future, I think going with solid state amplifiers is a must. And there's a growing industrial base for this now.
Is it possible to have peripheral scattering so that you study the photon scattering as a result of this?
Which scattering, sorry?
Like highly peripheral scattering for the electron and the ion, so that you can use it to study photon scattering. Similar to a lead ion scattering that was used to put constraints to the Born-N field.
I'm not sure I understand. So you want to have electrons getting scattered at the hadron, emitting a photon, and the photon then. Yeah, I think this is probably in the range of the physics program. Yeah.
Yeah, it's possible.
Yeah.
Yes. Hi. So this is, as far as I understand, this coherent electron cooling is new, right? This is.
Yes.
And what is sounds very interesting. So how dependent is it on the beam energy? Is it equally efficient for the low and the high end? And could you even go to much higher energy if it is efficient there?
So going to, your last question, going to high energy, of course, is possible. Of course, the more bandwidth is required, so it's getting more difficult. The cooling times would probably be longer, and certainly not going to get easier at higher energy. But on the other hand, if you go much lower in the present operating energy, then it's also the strong hadron cooler loses in efficiency. So at the moment, we have solutions for 275 GeV hadrons, 400 GeV hadrons. There's hadron energies as low as 41 GeV. That probably we cannot do that with the present cooler design. But what we intend is to boost the low energy cooling up to 41 GeV, which is feasible, and cool then use bunch beam incoherent electron cooling to cool a 41 GeV beam.
Thanks.
Yeah. There are further questions. What is the time schedule for this?
Okay, so the amplifiers will be procured. We will start procuring them in 27 time frame, but when we start operating the machine, we have to do so with fairly modest electron energy for the sake of the machine, to make sure we don't blow it up right away. But also the detector is not able to take full beam. It will take some time to learn how to deal with this and how to set up, to work with the detector, minimize backgrounds and so on. That's why we said we don't need the full build out of RF power on day one. So we stretch out the procurement of the RF power until fairly close to the end of the project. And when we start to need more power, that also helps us with the funding profile. It keeps the maximum funding request at a reasonable level, which is realistic.
Okay. Hello.
Yeah.
Hi. So what are the other physics goals EIC is having apart from the spin structure of proton that you have mentioned?
So this is the main focus is really hadronic physics. I mean, the question on gluon saturation, of course, overlaps somewhat with interests in the high energy physics community, but for the rest, it is nuclear physics. A large part of the community is interested in hadronic structure. How do the nuclei look like? How they are distributed? So typical nuclear physics questions.
Okay, let's thank the speaker again, actually. Yeah.